Okay, hello and good morning, everyone. Thank you for joining us. So, meanwhile, everyone is connecting, I will be introducing our special speaker, Dr. Elvira. Elvira received her PhD in chemistry in 2017, and her doctoral thesis was focused mainly on the preparation and analysis of nanocomposites properties in polymer matrices and graphene-related materials. She did her work in a research center called Interchemica in collaboration with the National Distance University here in Spain. The work includes the characterization of different graphene materials, such as graphene oxide and reduced graphene oxide, and understanding its features to maximize the processing of these materials in thermoplastics and thermoset matrices. A little bit about her background. Elvira has a strong background in nanomaterials and nanocomposite preparation, employing graphene-related materials. She's a co-author of multiple scientific papers about graphene materials, and she has been involved in more than 25 international conferences. Currently, she oversees multiple research projects at different levels in collaboration with the technical department of Avanzare, working on a national and European level. So Elvira, the floor is yours. Please go ahead by sharing your presentation.
Okay, thanks, Boyan. Thanks also all of you to coming to this workshop. Can you hear me?
Yes, I can hear you and we can see your slides. Go ahead.
Okay. So if you agree, let's start. As Boyan said, today the focus is on thermal conductivity, especially in these new materials that we are preparing containing graphene nanoparticles and show high thermal conductivity. To say today we are going to talk about this thermal conductivity, its mechanism, how we are working to determine, because surely you know there are different methods, and we will try to understand this and how graphene is moving the heat from one part to other. So we will explain some features of these materials which are critical for increase the thermal conductivity. And then we will present some applications in different kind of materials, thermoplastic, thermosets, rubbers. And finally, we will comment some challenge and the future in this area. But firstly, I will present Avanzare to all of you. Maybe most of us already know you. We are a Spanish company. We are located in the north of Spain, in La Rioja. We have more than 10,000 square meters for production plant with a large part dedicated to graphene and its scale up. We are composed by a full equipe of research and development people, PhD, mainly in chemistry, but also in other areas. And we are really focused on preparing innovative additives. So our products are made 100% in our facilities. And what we really do is develop these especially additives for rubbers, plastic, coatings, and resin. We provide to our customers with this high performance and advanced material. And we are usually working in different markets as automotive, paper, cardboard, footwear, packaging. Our applications are now in broad areas of the market. So apart from the graphene, which is going to be the focus today about thermal conductivity, and also we will see some of the electrical features, we are also strong in anti-static materials. We have different solutions for safety and anti-static rubber, thermoplastic, thermosets. And in apart from both thermal and electrical conductivity, we have a brochure of flame retardant additives, antibacterial, chemical tracers, and other specialty additives. In the world, we are present, we are selling now in about 15 countries. So we, as I said before, are located in Spain, in the north of Spain, but we have a commercial and product manager in Europe, in India, China, and also in America. So once that we have seen a bit from Avanzare, I'm starting about the thermal conductivity. I want to explain that in a non-metallic solid, as in the case of graphene, the heat is moved from the hot part to the cold part thanks to the vibrational waves in the lattice. So this movement is made by quasiparticles, which are called phonons. These phonons are generally are continuously generated at the heat part and transport to the cold part. So the move of these phonons is usually determined by the crystallographic defects. And as we will see after, it's really important in the case of graphene. When we put graphene in a material, we assume that graphene is conductive. Indeed, the intrinsic thermal conductivity of graphene is about 2000 watts per meter Kelvin, while the polymer matrix usually is about 0.2 watts per meter Kelvin, so difference is about 10,000 times. So when we put the graphene layers in a matrix, we need to ensure contact between these layers to ensure that phonons move. When we put these layers in the matrix, we can be in these three situations. In this first situation, there is no enough graphene layers to have contact between them and let the electrons or the phonons move. So there is no electrical or thermal conductivity. In the medium situation, we are in the situation that is usually called percolation threshold. And here, the electrons can move from one layer to other because of the tunneling effect, in case in which there are not perfect contact between the layers. So we have electrical, but not thermal or not so much thermal conductivity. In the third case, we have a very good contact between the layers of graphene, so the phonons can move easily, and we have electrical and thermal conductivity. So please keep in mind this feature, because when we are talking about increasing the thermal conductivity in a composite thanks to graphene incorporation, we will be in this situation. Okay. So once that we have understand a bit about how graphene is acting in a composite, I want to explain this of the family methods to measure the thermal conductivity. Let's say there is two big families, which is the steady state techniques and non-steady state techniques. This one, as the name say, is not measuring the thermal conductivity in the equilibrium, but during the heating process. So this is quickly way to measure the thermal conductivity, but as we will see after, there is some effects in case where the filler is of higher conductivity respect than the matrix, like in case of graphene, where the particle thermal shooting can occur, and it can be a source of error because it is translated in an overestimation of the thermal conductivity. In the case of steady state techniques, it usually records the thermal conductivity during the equilibrium. So it's most accurate, it's considered a most accurate method. However, it's more time consuming. This is just to show you an easier configuration. For example, a laser, which is in most of cases the most used source of energy, makes a pulse, a heat, about 1 milliseconds to the specimen that we can measure, and the temperature is recorded at the back. So this is usually the technique used for the transient methods. However, today I'm focused on steady state methods because it's most recommended for this kind of materials, as I said. This is the one that we have at Avanzare, and I'm showing you in a video how we technically do the measurement. This is with a cooling unit system to give this plate at cold temperature, about 5 Celsius degrees, while this upper plate is heated at about 45 degrees. So here inside we have some thermocouples to determine the voltage and, with that the temperature. So how is working this apparatus? This is working with standards made of stainless steel and Vespel, which is a plastic, a polymer with perfectly known thermal conductivity. So with different thickness standards, we can build this calibration curve. And in here, in this calibration curve, we insert our results of our samples to determine the resistance and, knowing the thickness, the thermal conductivity. So the kind of specimens that are required to determine the thermal conductivity by this method, which is based on a standard ASTM E150 and 30. We are using this kind of a specimen, which is flat and parallel faces of 5 centimeters of diameter, and we can provide to our customers, in case of a need, to the molds for inject the samples. Okay. In case that we are working with fluids, we have this special cell with same dimensions. We fill with the sample here and we put inside. This is the video of how we are measuring. This is a specimen with these flat and parallel faces. We are applying this special silicone paste of high thermal conductivity. It's necessary to apply directly with your fingers to create this irregular surface, as you are going to see now, to avoid any loss of heat from the sample to the upper and lower plate. So we put this silicone paste in both sides of the sample, and we insert in the cell. So once that is insert the cell is perfectly closed to avoid any loss of heat, and after 20-30 minutes, it's reached the equilibrium and it's recorded the voltage and so the temperature of the upper and lower plate, as you see here. So now it's placed. Remember that this is the hot plate, the down is the cold plate. We closed with some pressure and it's perfectly closed. So just to finish this section is to understand that there is a lot of standards, lot of apparatus, lot of theory, different comparison, some papers talking about difference in the same sample of the thermal conductivity recorded by different methods. So it's necessary to take into account that for comparative results, the method needs to be the same and take into account some overestimation due to, in case of transient methods. So once to know how to proceed, I'm talking about what graphene can do for this increase of thermal conductivity. I'm going to explain some features that are important to take into account when we are selecting a material for increase the thermal conductivity. If we compare the intrinsic thermal conductivity of carbon family nanoparticles to other, for example, metallic or ceramic, we see that the carbon ones are higher than the others. But not only this, for example, it's typically assumed and published in different papers that for thermal conductivity values of about 1 watt per meter Kelvin, some loads, and for example, boron nitride, which is the most efficient in case of ceramic ones, is needing about 50 to 80 volume percent to increase up to 1 watt per meter Kelvin. So it's a high quantity of load. In case of graphene, not only we can reduce this quantity, but also I want to remark the difference. For example, if we compare density, if we compare graphene density about 2 grams per milliliter with metallic nanoparticles, we are talking that this is about 2, 3, even 5 or more times higher. So this means that the density of metals makes that same percentage by weight, the molar fraction is much lower in the case of metallic particles. This is can graphically observe. If you remember, this is the situation that we need to obtain to have thermal conductivity. The graphene is dispersing and occupying much more than metal nanoparticles because of this. So once that we have seen this, if we go to modeling and to some theory, if we could orientate all our layers of graphene in a parallel way to the heat flow, this could be really efficient and the move of heat should be very high. The thermal conductivity should be very high. In the other case, if we put in the other direction, the efficiency in moving the heat is going to be extremely low. What is happening in reality is the distribution of the nanoparticles inside the matrix is random, and it's needed to go to complex models, and also the results are usually in the middle, both for experimental and for simulation. I'm going to explain three features of graphene which are really important. This is the defects in the structures, the lateral size, and the thickness. Ideally, all of us, when we read the definition of graphene, think in this perfect honeycomb of carbon disposed with an sp2 hybridation. However, when we prepare graphene, the process and the reality is that we have some defects due to different process aspects. So what we can see when we analyze the surface of a layer of graphene is that, of course, we have this perfect zone in green region with these graphitic structures where electrons and photons can move easily, but we also have these regions with defects. The defects can be due to the sp3 hybridation because of there are oxygen mainly, can be other atoms, but mainly are oxygen. And in this case, the carbon here is not in this sp2 hybridation, but sp3. So this is avoiding the movement of electrons and photons. Also, we find the end of the layer. So this is at defects positions. And also there are areas where there are not carbon atoms, there are vacancy defects. So independent of the way, but all these defects are affecting the movement of electrons and photons, and for that decreasing the thermal conductivity, also the electrical, but in this case we are focusing on thermal. What we do to analyze the quantity of defects of a material is acquiring Raman spectroscopy, Raman spectra. Here is myself together, my colleague Boyan, working in the characterization of some graphene. For example, you can see here in the spectra two typical bands associated to the effective positions. This is called the band, and as higher intensity, more quantity of defects. I need to say that there is a lot of theory about this technique, but to have a first approach to this, as much intensity has this band, more quantity of defects. Also, to the band is important to analyze the quantity and the quality of the graphene. But in summary, we need to have a graphene with low oxygen, because oxygen is the main defects present in link with the carbon. So we need to have low oxygen and defects content. We need to have large as possible sp2 areas with small sp3 domains, and with a large distance between the defects to let that in these high parts with sp2 hybridation, the electrons, and in this case the photons, can move easily. The second feature that I need to highlight is the lateral size of the material. Okay, both in modeling and experimental. For example, if we compare 100 microns lateral size to 1000 microns lateral size in the same kind of material, the difference is 2, even 3 times higher, because the lateral size, as higher lateral size, more easy is the movement of the photons. Both in experimental results, we can observe that a small platelet of about 2 microns in the lateral size is almost increasing the thermal conductivity, while a platelet with about 40 microns in the lateral size, as much as we are putting and we're increasing the percentage of weight of this nanoparticle, the thermal conductivity is increasing significantly, in this case up to 3 watts per meter Kelvin. So to see another example to analyze this is a recent paper of natural rubber working with different carbon blacks. We can observe the morphology of the aggregates of these carbon blacks and the thermal conductivity of these samples according to the percentage of volume of the load. If we compare these results with some obtained in natural rubber with materials from Avanzare, we can observe that there is a significantly increase with a lower quantity of this material. Why can we explain this? We can explain this because this kind of materials is about 40 microns in the lateral size, while this one is less than 50 nanometers, and even the aggregates has a smaller lateral size. So this is like if we compare a meter to a kilometer, it's the same range from nanometer to micrometer. The third important aspect to take into account is the thickness of the material. If we take into account that graphite is also a good candidate to increase the thermal conductivity, because it also has intrinsic high value of this thermal conductivity, we need to understand that graphite is composed by millions of layers of graphene. So, of course, the contribution in the XY plane is high, is 2000, the same, but also it exists an important contribution in the theta axis, which is about 6 watts per meter Kelvin. So, in case of graphite, this is reduced. And especially if we compare with graphene, the contribution in the XY plane is much higher than in the theta axis. Besides, in case of graphene, there is more number of particles because it's an exfoliated material in comparison to graphite. So once that we have understand these three main features, we are going to see some effects. Apart from the thermal conductivity, I'm going to explain that the electrical conductivity, as surely you have read and observed in some results, is increasing a lot. For example, in peak matrix, we are achieving 1 Siemens per meter in these composites, while the thermal conductivity is more than 0.5 bytes per meter Kelvin. So this is due to the tunneling effect and the movement of the electrons along the matrix. What happens when we need when we want to have thermal conductive composites but not electrical or electrical insulators? In this case, what we are doing is achieving it mixing our graphene nanomaterials with ceramic ones. As you've seen before, ceramic ones has also high thermal conductivity and at the same is electrical insulator. For example, boron nitride is about 10 to minus 8 Siemens per meter. So what we can do is allow phonons move, but put in the middle these nanoparticles, in this case the ceramic nanoparticles, to avoid that electrons move and have high electrical conductivity. Apart from electrical and thermal conductivity, I'm also say, as you surely know, that these materials has effect also in mechanical properties or another application, as for example, the flame retardancy. Here, what we are observing is different percentage of weight of graphene material and in combination with other flame retardant materials. So we can obtain about 1 Siemens per meter, near to 1 watt per meter Kelvin, and UV0 according to UL 94 fire regulation. So with this formulation, what we are doing is prepare materials, for example, for automotive application, or as we will see after, building sector, which is has a good classification according to fire, so self-extinction after a lot of time, because thanks to graphene, we are improving the performance to fire because the char formation of the surfaces. So now we are going to explain a bit about how to produce these high thermal conductivity samples and some applications, some real applications that can be obtained and are being prepared in different materials, as can be thermoplastic, thermoset, rubber, or fluids. So when we need to prepare these high thermal conductivity samples, we need to remind that, for example, if we have chosen this large lateral size graphene material, one thing that we should not do when we are processing with our polymer or our matrix is break the lateral size. Because, for example, if we put this in a dispersion mediated by balls, these high impact are going to break, are going to damage this plane and will cut it. So what we have at the end is not this initial dimension, but a smaller one. So the percolation, we will require much higher dose than the expected. So it's necessary avoid break the lateral dimension. Also, it's necessary avoid the reagglomeration. For example, in these same micrographs, we can observe that here in all the matrix, we have some parts filled with graphene reagglomerated, but others are empty. So if we take in mind that to have an homogeneous material, we have to achieve this surely would not be a good idea. Other aspect to take into account is have a good interface with the matrix, because as better is the interface, lower will be the resistance due to this interface. Okay, so the dispersion and integration with the matrix is really important to take into account. Some applications that we can observe in different areas, for example, this is thermoplastic. This is what we are seeing in the image is two materials need polyamide 6 and one polyamide 6 with graphene. So what we do to see graphically how this is working for heat dissipation and management is heating at the same temperature. At the initial time, you see that it's up to 100 Celsius degree. So we record the temperature with the infrared camera, and after 2 minutes, what we see is that the neat polyamide is remaining at about 70 Celsius degree, while the reinforced with graphene is 20 Celsius degree below. So this kind of applications is useful for accelerated cooling processes of materials. This is because these applications in polyamide is near to 2 watts per meter Kelvin, where we are adding these graphene materials. And in some cases, depending on the process, depending on the kind of polyamide, we are going up to 3 watts per meter Kelvin. So what we can do with these kind of materials is prepare this kind of polymer heat exchangers, as for example what you can see here, these pipes, these cooling hoses, radiator tanks, all of this, and the heat that we are changed with the fluid is more heat interchange and in a quicker way. What we do in these cases, for example, is prepare also if the customer needs is prepare a master batch with a high quantity of our material. This master batch can be 3, 4, depending on the processing on the starting polymer batch per meter Kelvin, and of course with high electrical conductivity. And what we can do is provide this master batch, because in some applications this is not required so much high thermal conductivity, but can be enough with one or more watt per meter Kelvin. So the user can be employing this master batch in the process to prepare a final material. As for example, this one that can be shown, this is injected mold for a tank, or a heat exchanger made of polymer instead of aluminium, with some properties as, for example, the reduction in weight. Okay. In case of thermoset, we've seen before the V0 behavior of the polymer in with glass fiber, fire retardants, and graphene materials, with these features of self-extinction, valid not only for automotive but also for building. For example, to manage the heat in houses, in passive house, and this kind of building. In case of rubber, we've seen before the increase of the thermal conductivity. These applications is especially done for sealant blocks used for anti-vibrational components in car and automotive industry in different parts of the car. And what we do is increase the heat dissipation. So these components are usually working at higher frequencies, so are working under an important fatigue, and accumulates a lot of hot. So if we reduce the working temperature of these materials, we are reducing the fatigue and we are increasing the life. It's important to highlight the results that we can observe here. This is the industrial formulation with different quantity of carbon black and different quantity pHr of our Avanthermal 440 conductive additive. In this case, for example, it's important to highlight that what is happening when we jump and when we increase a lot the thermal conductivity is that we are creating a very good, a very cohesive network with graphene nanoplatelets and the aggregates of the carbon black. So it's really efficient to move the heat from one part to other. Apart from solids, thermoplastic, resins, as we have already seen, there is some applications in liquid. For example, this is in water for cooling circuits. We have been working in different projects to have a nanofluid without affecting as much as possible the rheological performance. In this case, it's water-based, because in this kind of circuits, it's important that the viscosity is not enhancing. So as we can observe here, the suspensions are really near to the water performance, not increasing the viscosity so much, less than 10 centipoises. And what we are doing is working in these traditional cooling circuits. We have selected a smaller, in this case, graphene related material, because we need to take into account that these parts are really smaller. It's about 1 millimeter. So with this application, what I mean is that we can adapt our materials to the applications to have this optimized performance. What we can observe is an efficient comparison to neat water, more than 25,000 joules per second in the change of energy. So this can be applied in thermal management, both in buildings, in cooling systems for vehicles, in other ways. If we compare the performance of water, which is the blue line, with the red wine, we are decreasing the temperature of the coolant at the exit of the radiator. In this case, was recorded in a car radiator in about 10 Celsius degrees, which is can be, or we can think it's not too much, but it's really efficient. So here it's the watts that we are increasing in dissipation, and it's important to understand that we are increasing the performance of this radiator so much. So with this, I'm finishing some applications that have been some examples in different polymers, and I'm giving two comments that we and other partners have received working with these materials. So when we propose to graphene to a company or in some project, sometimes we hear, okay, but these materials are difficult to integrate. At Avanzare, we say, no, these materials are not difficult to integrate. It's just necessary have knowledge and experience. So we are glad to say that we have years of experience working of these materials. So as I said in some examples, we are not just providing the powder form material, we are providing a suspension, a concentrated master batch in different matrix, rubber, thermoplastic, a concentrate past in case of a resin or a epoxy, polyurethane. So in this way, we customize to the needs of our customers, and also we are avoiding other problems with healthy or with environmental exposure, and make easier to the final user, so they can optimize in their preparation of a final product. The other aspect that is usually commented is that these materials are too much expensive. But if we take into account that Avanzare is a company that has devoted large quantity of effort to make an efficient industrial scale up of these materials, we need to highlight that some of them has a very competitive price, because we are talking about that we can prepare even tons of this. So these materials are not so expensive, can be in the range of a carbon black, of a conductive carbon black. Indeed, if we take into account that usually the dosage that we are using are smaller than other typically employed in the industry materials, we are talking about cost-effective materials. And also, if we take into account that we can obtain other functionalities. So just to finish, we have seen these examples, and I also want to present this. This is a tank prepared with glass fiber and epoxy vinyl ester resin by industrial process. This is a filament winding, and this is a tank which is replacing metal tanks used for ATEX atmosphere, and is improving the corrosion, and is dissipating the charge to be used in ATEX atmosphere. So this is just an example that we can provide from Avanzare functional and coherent applications for the market. Of course, always thinking in cost-effective materials, which can be industrially produced. So I think now it's the moment of the questions. And just say you that if any one of you needs to contact, there are different email address to do it.
Okay, so thank you so much, Elvira. This has been very interesting. There are some questions in the chat as well as in the Q&A section. There is the first question from John, is asking, in rubber applications, you apply a normal mixing process like in an internal mixer. So in such a process, the graphene structure would not be broken in terms of defective.
We have experience in mixing in Bamburi, the typical mixer. We also have experience in do it by some kind of extruders, and at this kind of mixer is not cutting a lot the lateral side. It's not, for example, I wanted to give the idea of the ball impacts, because this is very high energy with lot of focus energy on exactly a point of the layer. But in case of Bamburi, it's not decreasing a lot, of course, in some, but not a lot, the lateral size.
Great, thank you. There is another question from Sanjay is asking, saying thanks for the nice presentation. Can you please comment on the films or coatings thermal conductivity measurements?
Sorry, thermal conductivity measurement that we could do, you say?
Can you please comment on the thin films
Okay.
or
Yeah.
coatings?
For thin films, sorry, because Boyan, because I did not understand you. For thin films, we can measure by the same method that I explained you, the warded heat flow meter. This is the one, the steady state that I show you in the video. The only point is that we need to reach up to 0.5 millimeters in thickness. So if the film is lower thickness than that, what we do is put more than one film to have this thick.
Okay.
But can be done, yeah.
Great. There is another question from Nicola, is asking, how does the mixing of graphene in rubber in the intermeshing boundary mixer, should we expect negative effects of cutting the lateral size due to high shear forces between the routers?
Yeah, this is I'm seeing this question, and also from Manel talking about the two screw master batch extruder. We usually use this kind, both Bamburi for rubber, both two screw extruder for thermoplastic. Not so much, of course, in some way, but this is an equilibrium. Okay, we have to disperse, not cut the lateral dimension, but properly disperse. So, for example, two screw extruder is a good idea to have a good dispersion, and break not so much as, for example, ball impact or another more negative process.
Okay, are there any more questions from the audience? Yes, so if you use, or there are more questions coming in.
Yeah, mono screw there in comparison with two. Usually it's preferable two. Also, it depends. It's not the same trying to disperse a small lateral size material, which maybe with less shear can be better dispersed, than a very large lateral size, which in some cases needs more shear to have a good dispersion. So it's not the same. Mono could be acceptable for some small platelets or some kind of graphene materials, but for others it should be better twin screw.
Okay, there is another question. Is there any chance to know how the W slash MK value that you need in the plastic, for example, to substitute metals?
The theory says one thing, but our experiences and in papers you can see that maybe to replace a metal you do not need to reach the intrinsic thermal conductivity of the own metal, depending on the application. Maybe if we are talking, for example, of about evacuate the heat, you could use a lower thermal conductivity polymer or composite.
Okay, all right. I think we run out of questions. Um, is there any more question? Does anyone have anything to add? Perhaps one question on a, like, if you can put us in some perspective for people that don't have a lot of knowledge on this type of materials. Why is it so important to have thermal conductivity in materials, to have materials that are thermally conductive?
Okay, now we are trying to, from the last decades, plastic polymer is really important components in many fields, and we are trying to substitute because some metal parts of typically made in metal can be prepared in polymer. However, we need to remind that metal is both electrical and thermal conductors. So, in some cases, mechanically, of course, we could achieve, or with some loads, we could achieve these mechanical properties and also some value of electrical conductivity. But usually, we are forgetting the thermal conductivity, and for many cooling systems, for many applications, we need to both for functionality and because in some fields, for example automotive, we are used to the handles of a car feel like metal, not like a plastic. So this feeling like metal is made because of the thermal conductivity. So to increase, not so much, but to increase, to have a medium, let's say, value that let us have this feeling, it's needed to increase the thermal conductivity, and graphene is really good candidates for this.
All right. Well, thank you so much, Elvira. It was a pleasure to have you, and thank you to all the participants.
Thanks.
Please remember that if you want the presentation slides or to view the recordings of this presentation again, we will be uploading that today or tomorrow latest on our YouTube channel. So we will be circulating that around as well. And for any questions or any other doubts, yeah, don't hesitate to contact us. You can see all the emails on the screen. We will be happy to answer that. For now, we wish you a good weekend, and until next time, thank you so much.
Thank you to all of you. Thanks, Boyan.
Bye. Take care.